Okay, good afternoon, everybody. Sorry for starting a little bit late. So let's get right into it. Today we are doing the iodine clock kinetics lab. Now, again, this week we have a data sheet to submit. So there is no lab report, just the data sheet. Okay, so today's learning goals are to understand how reactant concentrations affect the rate of a chemical reaction. So this should give you a clue already as to what the order of our reaction will be later. So foreshadowing. We are going to observe how temperature can affect the rate and the rate constant of a reaction. We are going to get used to some rate equations. We will be using the Arrhenius equation as well, and we will linearize some exponential functions. Okay, so today's lab does have quite a few mathematical concepts in it. So we are going to go through rate laws, rate constants, and reaction orders. We are also going to discuss the Arrhenius equation and linearization of an exponential formula. So we will be using a little bit of pre-calculus today. Okay, so the chemicals that we are using in today's lab, we are using hydrogen peroxide. So it's used as a disinfectant. You can get various percentages of hydrogen peroxide in your local grocery store or pharmacy. It does undergo a spontaneous decomposition to H2O and O2. So that's why sometimes when you buy like higher percentage of hydrogen peroxide, it'll come in those bottles that have like the bevels in them so that they can expand as it decomposes. Otherwise, you might have an exploding bottle of hydrogen peroxide in your bathroom cabinet. We are using hydroiodic acid, HI, which is a very strong acid when concentrated. So HI is one of our strong acids. Iodine is our product, so it's also commonly used as a disinfectant. So especially if you are working in the healthcare world, such as like a hospital or doctor's office, iodine is often used as a disinfectant. And we know when iodine is being used because it has a dark brown color and it has like a very specific odor to it. We are using thiosulfate in this reaction. It is a reducing agent. And we are using a starch indicator. So the starch in this reaction will react with, complex with the iodine to make the dark iodine color even darker so that we are able to notice iodine production immediately. Okay. So today's reaction, the oxidation of iodide is the ion, iodine is the I2, elemental I2. So we are oxidizing iodide into iodine, and the hydrogen peroxide is being transformed into water. In addition to H pluses. At the same time, we are doing a secondary reaction where the iodine is being consumed by the thiosulfate. So why are we doing this secondary reaction? And so let's go to the next slide. So we want to know exactly when iodine will be present. And iodine, the hydrogen peroxide reacting with the iodide is slow, whereas the thiosulfate reaction with iodine is very fast. So as soon as iodine is produced by the first reaction, the thiosulfate will be used up. Now, we need a way to measure how much hydrogen peroxide and iodide are being converted. And we can do that by using a third molecule, and that third molecule is thiosulfate. So we are using thiosulfate to consume a known amount of iodine. And so at the point where we start seeing the dark color of the iodine, we will know exactly how much hydrogen peroxide and iodide have been consumed, because as soon as we've seen that brown color appear, we will know that the total amount of thiosulfate that we put in there will be completely consumed. So the thiosulfate is a way for us to know exactly how much has been consumed at a certain time. So if we did not have that third molecule, that measure, there would be no way to know how much hydrogen peroxide and iodide had been consumed. So that is why we have the thiosulfate. Okay, so once we know how much has been consumed, we will be timing from the point where we add the reactants together and until we see the brown color appear. So we will be measuring a time, and we will have a known concentration based on the sulfate. So we will be able to calculate the rate of the equation. And so in physics, we think of rate as distance versus time. In chemistry and biology, we think of rate as amount versus time. And so the rate of a chemical reaction is dependent on a lot of different things. So the concentrations of the reaction being one, the order of the reaction, and the value of the rate constant. So there are some reactions, depending on how they operate, some reactions don't depend on concentration at all. Those are called zero order reactions. Some reactions only are dependent on the concentration of one of the components. That would be an example of a first order reaction. And some reactions are dependent on multiple concentrations of things, and that would be an example of a second order reaction. So in today's lab, we will be figuring out what the rate of the reaction is. We will also be determining what the order of that reaction is. So is it concentration dependent or not? And then we will also be able to determine what the rate constant is. And so we will also see that the magnitude of the rate constant K varies with temperature. So a few of our reactions will be performed at different temperatures while maintaining the same concentration of our reactants. And the units of the rate constant are dependent on the overall reaction order. So you will see in the makeup data that there is an error with the rate constant units, but we will discuss that later. Okay, so the reaction order. So when we're looking at the rate equation, we have rate equals K times the concentration of A to the power of A times the concentration of B to the power of B. So A and B are the reaction orders. And so the reaction orders show how the concentration of each reaction affects the rate. So the sum of A and B is the overall order of the reaction. So if a reactant, if reactant A has an order of 1 and reactant B has an order of 0, the overall order of the reaction would be 1 plus 0 equals 1. If both reaction orders were 1, so if A was to the reaction order of 1 and B was to the reaction order of 1, the overall order of the reaction would be 2, because 1 plus 1 is 2. So the order of the reaction are usually small, so it's usually 1 or 2, 0, 1 or 2, and it's always a whole number. Okay, so now let's talk about the Arrhenius equation. So the Arrhenius equation is the rate constant K is equal to a frequency factor, to times E, so to the negative EA, which is the activation energy, divided by RT, which is the gas constant and temperature. So temperature is in Kelvin, and because we are talking about energy, so energy is depending on what our units for energy are, will determine which gas constant we are using. So we are going to be manipulating the Arrhenius equation by taking the natural log of the equation. So let's go back here. So we have a few things going on. So K is alone on one side. So when we take the ln of K, it's just ln of K. So on the other side, we have A times E to the power of something. So when we have that multiplication there, when we take the ln of a product like this, the ln of a product is the sum of the ln's. So we have the ln of A plus, you could think of this as the ln of E to the power. So the ln of E to the power is just what the power is. So if we go back here, the power of E here is negative EA over RT. So ln of E equals 1. So if we were to write this out, let me just bring up the whiteboard instead of trying to describe it to you. All right. All right, so we have K equals A times E to the power of negative EA over RT. So when we take the ln of both sides, we get the ln of K, and then we have to take the ln of this. And so this becomes ln of K equals the ln of A plus the ln of E to the negative EA over RT. And so that is, you bring the power out in front, so it would be negative EA over RT times the ln of E, and the ln of E equals 1. So this is just ln of K equals ln of A minus EA over RT, or we can rearrange it. So it's ln of K equals negative EA over RT plus ln of A. Okay, so Now let's think of this as an equation of a line. So y equals mx plus b. So ln of k is the y, ln of a is b. And so now we just have to figure out what the slope is. So if you remember from what I said before, we will be varying temperature. So that means our x is always a dependent variable. So a dependent variable is the thing that you are changing in your experiment, and y is your independent, x is the independent variable. So that is what you're changing in the experiment. Y is our dependent variable because the outcome of y depends on x. So the ln of k is our dependent variable y. X must be what we are varying. And if we are varying temperature, that means we can separate out temperature from our this part of the equation. So ln of k equals negative EA over R times 1 over T. And it's 1 over T because T is in the denominator here. And then we have our ln of A. So in this equation, this is y equals mx plus b. We have our x and we have our slope. So when we graph our temperature dependent trials that have the same concentration, we will display the equation of the line that we have graphed based on our data, and the slope of our line is going to be negative EA over the gas constant, and our variable x will be 1 over T. And so that's how we will do that later. Okay. All right, so the procedure overview, we will obtain all the solutions. They are pre-made. So we will have a solution of iodide, we will have a solution of hydrogen peroxide and DI water, as well as a thiosulfate starch indicator solution. So the first 3 concentrations of hydrogen peroxide will be varied. The 4th and 5th trials will have the same concentration as trial number 3, except the temperature will vary. So here is our setup. We have the thiosulfate and starch. We will have the hydrogen peroxide and the hydrogen iodide. We will do the first 3 reactions in an ice bath. So the temperature for our first 3 reactions will be 0 degrees Celsius or 273 K, I believe. Let's take a look. 293. That would be room temperature. Okay, anyway. Wait, what? All right. So, in this reaction, once we add all of the components together, we are going to start a stopwatch, and we will stop the stopwatch until we see the color form, and that's when we know that all of the thiosulfate is reacted. And the change in the thiosulfate concentration is equal to half of the change in the iodine concentration. So we will use that to figure out how much iodine was consumed, and therefore how much hydrogen peroxide was consumed. Okay, so the general rate law for this experiment is the rate, so concentration over time, equals the rate constant times the concentration of hydrogen peroxide to the power of A times the concentration of H plus to the power of B times the concentration of iodide to the power of C. But the concentration of hydrogen iodide is kept constant over all of the reactions. So we want to know what the order of the reaction is for just the hydrogen peroxide. And so our rate is going to be equal the rate constant times hydrogen peroxide to the power of A. And we can linearize this by taking the log of everything. So this is similar to the Arrhenius equation where we took the natural log of everything, the ln, but in this case we're doing the log. So the log of the rate equals the log of the rate constant plus A times the log of the concentration of hydrogen peroxide. Okay, so some of the calculations that we're going to do. So the rate is the change in concentration over time. K is the rate constant. The concentration of H2O is the brackets signify concentration of something. And A is going to be the order of the reaction. Okay. Okay, so again, we're doing a worksheet. It needs to be handed in. I will extend the time if it's not already extended to, what's today? Tuesday? Till Friday, I think you guys submit on Fridays. Okay. Safety in the lab, we would be wearing gloves and goggles, and we would be working in the fume hood. And then everything in this lab we would dispose of in the proper waste rather than the sink. So especially when you're working with the halogens like iodine and iodide, those have to be disposed of in a particular way because they can be hazardous to the environment. Okay, so now let's go ahead and watch the video. Oops. Where is it? Where is it? Where is it? Here we go.
All right, so this is the pre-lab lecture for the iodine clock experiment that you all would be carrying out if you were here.
We're going to skip over Paul. Sorry, Paul.
Error is never a source of error and should not be listed as such. Chemists are perfect, we make no mistakes, we always have to blame our instruments for any issues that would occur. And that's all I've got. All right, so to begin this experiment, I have my hydrogen peroxide, my hydroiodic acid, and my sulfur-containing compound with starch in it. What I'm going to be doing is I'll be following this table here for how much of each solution I add to each test tube, going through runs 1 through 3 at this desktop here, this bench top here, because we're going to be working at room temperature for trials 1 through 3. I have the temperature for trials 1 through 3 here. Each of these are 22.7 degrees Celsius, 1 through 3, that is the temperature of the reaction. All runs will involve you filling a test tube up, and once everything is filled up, all of them will have a volume of 2,000 microliters or 2 milliliters. So when you're doing M1, V1 is equal to M2, V2. These values are going to be your your V1, and your V2 is going to be 2,000 microliters. What you need to do is you need to figure out M2. You should have the concentrations written down in your printout, but if you are uncertain of them, they are at the top of my table here. The concentration of hydroiodic acid is 0.1 m. The concentration of hydrogen peroxide in the container, not in the test tube, is 0.20 m. And the concentration of my sulfur and starch solution is 0.15 m. So I'm going to be going ahead and carrying out the first experiment here. I will need to have 3 different tips because I have 3 different solutions. You should never mix tips. Each of these were cleaned before we began, so they will be soiled only after this experiment. The way that we start this is we have our test tube labeled 1 for run 1. We are going to dispense the correct amount for run 1 of each of these solutions here. So that is 400 microliters of hydrogen peroxide first, followed by quick introduction of both hydroiodic acid and our sulfur-containing compound. I do, however, notice that I have forgotten that in trials 1 and 2, we need to add a certain amount of water. So what I will be doing really quickly is going and obtaining some room temperature deionized water. It's important that all of our solutions have the same temperature so that we do not have any fluctuations in temperature. A good source of error for this, though, is that I am handling all of these solutions, and as I handle these solutions, I am applying body heat to the solutions, thus making the temperature inconsistent. Also, another good source of error is hydrogen peroxide itself deteriorates when exposed to UV light. That's why it's always in those nice opaque brown bottles. You don't want to have UV light present in your sample or present to our hydrogen peroxide, otherwise it readily deteriorates. Meaning the concentration that I started with is not currently the concentration in there. Mind you, it's very slow reaction, but it is a reaction that occurs when exposed to UV light. So I'm going to first start by putting my water and hydrogen peroxide for trial or run 1 into a test tube. These are not going to react with each other, so I don't have to worry about the reaction beginning to occur. So I'm starting with 400 microliters of hydrogen peroxide, just making sure I'm following everything correctly. Yes, 400 microliters of hydrogen peroxide into run 1 test tube. I pressed the first stage, not the second stage, take in my solution, which is 400 microliters. Place this into my test tube. Clear out all of the remaining solution. And then I want to swap out this tip and move to my water tip. I actually needed 4 tips because I have the additional water added. I checked that I need 400 microliters of water as well in this test tube. Press to the first stage, collect my water, and place this into trial 1. Now I'm going to need the help of my camera worker to observe, to start the timer when I add my hydroiodic acid and my sulfur-containing compound, because the reaction begins to happen fast. Now, while this reaction is happening, I want to be agitating my test tube so that all of the components are mixing thoroughly and are given the proper chance to interact with one another. I need 1,000 microliters of hydroiodic acid. I have that set. And I need 200 microliters of my sulfur compound. Is that thiosulfate? Correctly. I will be using, let's see, what organizes properly. For iodic acid, I have my tip. This is my 1,000 here. All right, so I will collect my 1,000 microliters of hydroiodic acid. I'm going to get to the tips really quickly because I have lost track of these. And if you lose track of a tip, just get a new tip. Don't ruin your experiment. So this is for my this is for my sulfur compound, and this is for my hydroiodic acid. I'm going to collect first my sulfur compound here. Now I'm going to get my hydroiodic acid in this, I bet. Now I'm going to be adding these rapidly and then beginning agitation. So as soon as I say go, start the timer. And go. Now what I'm going to be doing is agitating this properly until I see a color change, and then the stopwatch will stop. So I'm making sure everything is getting sloshed around in there. The two reactions are occurring simultaneously, and it should change after a certain amount of time. This agitation is extremely important. If you don't have proper agitation, the reaction will not occur in the actual time because you're not giving everything a chance to actually interact. The reaction will be almost instantaneous, or the color change will be instantaneous. The reactions are, of course, occurring. Taking sweet time. Trust me, this is as much fun for me to watch as it is for you to watch.
Jeopardy theme song.
Do it? Oh, no. How long has it been?
Minute 40.
A minute 40? Something is wrong. Or maybe not.
2 minutes.
Yeah, I don't remember. I don't recall these reactions taking that long. All right, we're going to call this one a bunk and redo it. That ain't going anywhere. All right, we're going to try this one more time. Wouldn't that be fun? So little issues like this do occur. That's why it's always good to be ready to restart as soon as you have a problem. Even when you're on an experienced test, you can always learn error. All right, let's try this again. Got my 400 microliter tip for my hydrogen peroxide. Run one. This tip. Tip for water. And to run one. Water.
Did the other one just turn brown?
Yep, it did. Okay, so it did happen. Sweet, sweet time. So I'm called it. So nothing was done wrong. It was just much slower than I recall it being. It's good. Now I can save face. But anyway, we're redoing trial one. As I said, I need 200 microliters of sulfate and 1,000 of hydroiodic acid. That's correct. Correct. Ooh, that took a lot longer than that. All right, and you ready to go? So you in and start. Let's try this again. So did that change like well into me creating this new one?
I just noticed it.
Oh, you just noticed. Sorry. That means that the cold one is going to take its sweet, sweet time.
Awesome.
But at least I don't have to be embarrassed about doing something wrong because I didn't do anything wrong. Just slow, slow, slow reaction. Shooting it up. Good news is that the other two should happen faster because we'll have a higher concentration of hydrogen peroxide. Oh boy. What time am I at?
2-minute mark.
Okay.
Probably about a minute left. Three-minute mark.
And there we go. So how long was that?
3 minutes, 6 seconds.
For 186 seconds.
Mm-hmm.
So run one at a time of 186 seconds. Get a new glove. Now that that is done, we can move on to run two. All right. Moving on to run 2. This is my hydroacidic acid. This is my parasulfate. Hydrogen insane. Yes, it is parasulfate. Excellent. All righty. This next trial, I need 600 microliters of hydrogen peroxide. 600. I'm going to collect hydrogen peroxide and move them back there so they don't get confused. 600 microliters of hydrogen peroxide. Check the price. Put them all in. Adding it to the test tube for trial 2. Place this tip. This one I only need 200 microliters of water. Everyone is enjoying their time online courses. 200 microliters of deionized room temperature water. Now I need 200 again microliters of our starch solution and 1,000 microliters of our hydroactive acid. So if you will ready the stopwatch, get this ball rolling. And go. Now another source of error is I am able to really agitate this at room temperature, but when we move over into our water trials and our hot bath trials, it'll be more difficult for me to agitate. And that'll throw things off a little bit, but I will still do my best to keep it agitated. Deal with something like that, instead of doing a hand agitation, if you have some sort of small stir bar and a hot plate that has the spin function, that would be a great way to mitigate that. And that should be occurring a little bit faster. We'll see. As I said in the pre-lab lecture, once that nice dark color forms, what that is signifying is that all of the thiosulfate has been consumed. So all of our changes in hydrogen peroxide should be the same as the amount of thiosulfate consumed. Because all we're doing is we're just monitoring the change in the hydrogen peroxide in a certain amount of time. So lines 5 should be in theory the same across.
Two minutes, 6 seconds.
2 minutes, 6 seconds. So a much faster time, 126 seconds. Under 26 seconds for trial 2. All right, good glove time. I'm just gonna bring this over here. right, on to run 3. Put 1, 2 back here. Brother. This is our iodic acid. This is our sulfur compound. This time for run 3, I need 800 microliters of 800 microliters of hydrogen peroxide. I might take 4 hydrogen peroxide. 800 microliters. To run through the test tube. That's it. I need no water for this one if I look at the table. So now all I have left is 1,000 microliters of my hydroiodic acid and my 200 microliters of my biosulfate solution. 200,000. All right. And go. This should be even faster than run 2 because it has even more hydrogen peroxide present. The last one was a minute faster, so this one could be a minute faster. We'll see.
Minute 32.
Oh, minute 32. All right, trial 3 took 92 seconds. And perfect. But now, see, because of the way that I was holding the test tube, I was applying body heat to it each time. So that is just one of the very valid sources of error. All right, so now we're going to move on to our temperature trials of this. You now have all of the data you would need to figure out your order of the reaction. By order of the reaction, we remember when we're trying to solve a rate law, what the order of the reaction is just this exponent up there. So now we're going to move on to our temperature trials of this. I will bring the tips that I used over because I'd like to keep my waist down. And this is so. All right. And this is difficult as possible. Seriously? Thank you. So we're going to first start with our cold water trial, I think. forward to that one at least. No, we'll keep it consistent. He wants us to do the cold trial. So we will instead do 1-4, which is our hot water trial. First, I need to observe the temperature of our solution, which is, oops, can't take you down. Typically, you should not put your head in the fume hood, but it's hard to read this without doing so. Looks like our temperature is 44. It's going up. Call it an even 45.0 degrees Celsius. So I'll write that down. 1-4. Temperature is 45.0 degrees. 45.0 degrees. That's all. You should never bring your work stuff into the fume hood. It is only for chemicals and the instruments that you are working with. All right, so I will consult my table. I need 414, 800 microliters of hydrogen peroxide, 1,000 microliters of hydroiodic acid, and 200 microliters of thiosulfate. So we'll start with the 800 microliters of hydrogen peroxide, which is this guy, right? Yeah. 800 microliters of hydrogen peroxide. So here is my 1-4 test tube. Here is my tip for hydrogen peroxide. And if I remember correctly, I need no water for these trials. That is correct. So I will quickly, I have to work quickly because I do not want much temperature change to occur outside of the unit. So that is another source of error, is that as I am transferring these solutions to this test tube, the temperature of the reaction chamber will be changing. Now I need 1,000 microliters of hydroiodic acid solution and 200 microliters of my sulfate solution. So 1,000 microliters of hydroiodic acid, 200 microliters of that. Start. Oh, I'm clicking start and go. Now, I want to keep the temperature consistent, so I want to have this reaction occurring in the correct temperature in a warm water, in a consistent temperature warm water bath. As much as I can here. This should happen very quickly. And we're done. Much faster. What was our time?
25 seconds.
25 seconds for run 4. So I'll write that down here. Run 4 at a time of 25 seconds. All right, on to run 5. Yes. Okie dokie. On to run 5. New test tube, and this one should take considerably longer than runs 1 through 4. This one is going to be done cold, in a very cold temperature. All right, this was my sulfate solution. This is my hydroiodic solution. The temperature for run 5 is going to be 0.2 degrees Celsius. So I'll write that down for my temperature at run 5, and my temperature is 0.2 degrees Celsius. Critically low, and it's a bit lower than I think originally set it to be. 2.5, they say 5 to 10 degrees Celsius. Screw that, we're going 0.1 degrees Celsius. Exciting. Okie dokie. So first I'm going to obtain my hydrogen peroxide yet again. I need 800 microliters of hydrogen peroxide. Ice cold hydrogen peroxide. Now, I need 1,000 microliters of hydroiodic acid. And 200 microliters of my biosulfate solution. That's got a nice bubble in it. Don't like bubbles. Clear. Alright, I don't trust you anymore. Good tip. Son of a fuck. Things get colder, they don't grip as well. No bubble. Excellent. All right. Ready to go? And go. Oh, never mind. Start it up again. This is why agitation is important. So we'll add 1 second on. Close that.
Seven and a half.
Shake and up. So reduce, take about 3 seconds off that.
So +1 -3.
Plus 2. I mean minus 2.
So 743.
743. So 700. Yeah, okay. So that's 743. Put this down here.
So 463.
Alrighty, our time for run 5 is 463 seconds. I suffered so that you do not have to. You should be able to calculate this using the M1V1 is equal to M2V2 formula. So row 3 is all M1V1 is equal to M2V2. Remember, M1 is this concentration here. V1 is whatever amount in microliters that was used from the previous table. M2, you don't know. V2 is 2,000 microliters or 2 milliliters, whatever you would like to work in. This, again, you need to use M1V1 is equal to M2V2 to find this. It is not just the same as that, but in this case, this will be your M1 for this formula. And then you should be able to easily relate our delta hydrogen peroxide to the initial concentration of S2O3, because the change in hydrogen peroxide should be correlated directly to our initial concentration. We don't see the reaction, the iodine reaction, occur until all of our thiosulfate is consumed. So this should be equal to some factor of 2 or divided by 2, depending on if you do it correctly. Value here. The rate is going to be your 5 divided by 1, row 5 divided by 1. As I said, you're going to be plugging in A is equal to 0, A is equal to 1, and A is equal to 2 to our rate law that was up on the board, or just the general rate law of the reaction. You'll plug A is equal to these values into that to figure out these K values here. You'll solve for K. Mind you, these should be K prime, but they were not written on there correctly. From these values here, you will calculate the relative standard deviation here. So these are all used to find that. Then you will use, this will be even more confusing, use these values here. You need to fill out all of these rows, but it will be the rows from these 3 that you will use to create your Arrhenius plot after you you'll use to create your Arrhenius plot and then linearize your data. And that should conclude everything that we did for the experiment itself. I'm going to go over the discussion questions really quickly to make sure that nothing catches you by surprise. You need to fill out all of this information. You can find your you need to include the slope of your Arrhenius plot, determine the reaction, determine the, what can I think of this word, activation energy of your reaction using your Arrhenius plot, your linearized Arrhenius plot. This is the calculations for it. This is what the actual value is. Make sure you're in the correct units. Carry your units through, making sure that you keep everything in either joules or kilojoules or liters or milliliters, just to make sure all of your units are consistent and cancel out properly. For question 1, it says, discuss and obtain your results for the relationship between concentration and rate. Are they consistent with your expectations? Be sure to include what you expected and why and how your data did not meet these expectations. Really just talk about whether or not your data from your relative standard deviation didn't match your linearization of your rate law. That's really what you need to focus on there. Discuss, for question 2, discuss the obtained results from their relationship to temperature and rate constant. Did they match your expectations? Would you expect a hot reaction to happen faster than a cold reaction? Think of this as, would you expect ice to melt faster at 100 degrees Celsius or at 2 degrees Celsius? And that should give you what your expectations should be. And they definitely, looking at the data, match those expectations. And then for question 3, list the likely sources of error. As I said, when I was agitating the room temperature samples, my hand was holding the test tube and applying body heat to it, which was more than the room temperature. Proper agitation is very hard to achieve, so even though I was vigorously shaking it, it was not as optimal as it could have been, and agitation within the temperature, the varied temperature reaction chambers or reaction areas was more difficult, so I wasn't able to agitate as thoroughly. And those should be your sources of error, and that should include everything you need. Just make sure you have everything for all of the questions here, as well as all of the questions on here. You just need to make sure that you have everything absolutely filled out before you take photos of this and send it all in. You will need to include photos of your plots in the submissions as well. And that is all that we have for.
Alrighty, so I know that was pretty long. Hopefully you guys are all still here. Looks like it. Okay, so let's just go through. Okay, so now let's go through the data. So I'm going to share my whole screen. Okay, so as Paul was talking about the M1V1 stuff, that has all been calculated for you. in the makeup data. So let's do some of the calculations together. All right. Okay, so we have temperature in seconds. So I know that in your data and analysis section of your manual, it says TAV is the calculated average time interval. So if we were doing this in class, we would have all of the data from all 8 lab pairs. And we would just take an average of all of the data that you guys collected together. But instead, we're just going to use temperature in seconds. So in the makeup data, it just says temperature in seconds. Okay, so let's go down to where it says row 5. So the change in H2O is the change in hydrogen peroxide concentration during TAV. So based on the balanced chemical equation of both of our equations, I2 is equal to the concentration, or the concentration of I2 is equal to the concentration of thiosulfate divided by 2. And the concentration of I2 is equal to the concentration of H2O2, or the hydrogen peroxide. So that means the H2O2 concentration is equal to the concentration of the thiosulfate divided by 2. So let's look at our makeup data. So based on the data that is provided to you, our row number 5, so let's start there. Our row number 5, every single run is going to be equal to the concentration change of H2O2 is going to be equal to 0.015 divided by 2, and this is molar. And that is equal to 0.0075 molar. Okay, so that is your answer for row 5, sorry. So now let's take a look at row 6. So now it's asking for the rate. So the rate has units of m over s, so molar over seconds. So that must mean it's the change in concentration over the change in time. So for run 1, the rate is going to be equal to 0.0075 molar divided by 207.6 seconds. So run 2, the rate is going to be equal to 0.0075 molar divided by 132 seconds, and so on. So the rate for run number 3 is going to be equal to 0.0075 molar divided by 103.6 seconds. Okay, so you guys get the idea. Now we need to figure out row 7. So the rate constant. So the rate equation is rate equals K prime times the H2O2 to the power of A. So, or on this page, in the makeup data, it's X. It doesn't really matter. So what we need to do now is fill in all of the different information. So let's take the rate from run 1. So let's go ahead and solve this. So 0.0075 divided by 207.6. That gives us 3.6 times 10 to the minus 5th meters per molar per second. Okay, so for run 1, we have 3.6 times 10 to the minus 5 equals K prime. Okay, and so the H2O2 concentration that we're using is not the change in concentration, but the total concentration available. So we want to use row 3. So in this case, it would be 0.04 molar to the power of X. So for row 7, we're setting X as 0. So when something is put to the power of 0, it equals 1. So for row 7, because all of the concentrations that we're going to put in are going to be reduced to this value of 1, rows 6 and 7 are going to be equal. So K is going to equal the rate when the order of the reaction is 0. So what that means when the concentration is when the order is 0, that means that the reaction rate does not depend on the concentration. So it makes sense. So that makes sense. So what about when X is equal to 1? So let's see what that looks like. So 3.6 times 10 to the minus 5 equals K prime times 0.04 molar to the power of 1. So K is going to be equal to 3.6 times 10 to the minus 5th divided by 0.04 molar, and this is in meters per second. Okay. So let's do this calculation. So this K value is going to be equal to 9.0 times 10 to the minus 4. And then it's going to be second to the minus 1 power because it's just per second. Okay, so now what about when X is equal to 2? So again, it's 3.6 times 10 to the minus 5 is the rate for run 1 equals K prime times 0.04 squared. So first, let's square 0.04. So 0.04 times 0.04. That gives us K prime times 0.0016. So K prime equals 3.6 times 10 to the minus 5 meters per, or molar per second over 0.0016. And since this was molar, this is molar squared. So this is molar squared. So K prime equals 2.25 times 10 to the minus 2, m minus 1, s minus 1. Okay, so you guys will need to do the same calculations for runs 2 through 5. And then you will need to do the relative standard deviation of a few of the runs. So let's take a look at what that is. Okay. So for the first 3 trials, 1 through 3, where we are varying concentration, in order to figure out what the order is of the reaction based on concentration, we need to figure out if there is less deviation between the K values of 0, 1, or 2. So we will take the relative standard deviation of the first 3 0 orders and figure out what that relative standard deviation is. We'll take the standard relative deviation of the when x equals 1 and the relative standard deviation when x equals 2. And whichever one is closer to 0, so the one with the least amount of deviation, that is the order of the reaction. Okay, so what is the relative standard deviation? What does that mean? So the relative standard deviation is the standard deviation divided by the average. So you will take the standard deviation of these 3 things and then divide it by the average of these 3 answers. And that will give you the relative standard deviation. Same thing with this one. You'll take the standard deviation of these 3 and then divide that by the average of these 3. And the same for row 9. Okay, and that'll give you your order of H2O2. And then once you do that, we can do the ln of K. And row 12. Let me see what I have for row 12. G5 divided by D5. Oh, okay. And then for row 12, all you need to do is convert Celsius to Kelvin, and then take the inverse of that. So 1 divided by what that number is for the inverse because we are going to be plotting, I'll show you my plot. We will be plotting the ln of k versus 1 over t to get this equation of the line. Okay, so at this point, does anybody have any questions?
Sorry, the closer the standard deviation is to 0, the order would be in that order?
Yes. So let me I'm just going to show you the calculations here. So in Excel, you can do the standard deviation of, so in this case, B12 through D12. So these 3 cells divided by the average. And you do that for each row. So this is row 12, 13, and 14. And so whichever standard deviation is closest to 0 is the order of the reaction. So you guys should see that the order with the smallest relative standard deviation is first order. Because we saw, based on the data, that as we changed the concentration, the reaction time also changed. So that tells us that it is dependent on concentration. Okay, any other questions?